Let's have a look now to another view of the charged particles dynamics simulation tools related to the different applications that we can also cover in our portfolio. The charged particle dynamics applications are really at the heart of the development of the new technologies. And you see here, for instance, this is the CERN particle accelerators that you have in between France and Switzerland. You can also nicely see here the Geneva airport. And then here you have already quite a lot of physics which is involved with this kind of big instruments. But it's not only about fundamental research. These applications are also related to emerging technologies and new applications that you will see also in the future in the different industries. And that's exactly what I will try to cover during these talks in order to provide you with some applications in the different industries. So saying this is the outline of my talks after a brief introduction of the CST technologies that we have for the charged particle dynamics area. Then I will show you some examples in the aerospace defense industry, energy and materials, high tech, life science, and then we will have a short conclusion. So let's start with the introduction of the CST technology. So the CST kernel is really here since the beginning, and the origin of CST is really coming from the particle accelerator. And in 1992, the foundation of CST was based with the first commercializations of the MAFIA tools, which is the Maxwell finite integration algorithm. And at that time, we were not able to solve complex devices without having a technology which is useful to be able to run on the PC on the machines that you have in this period. And then following the technologies, we have introduced in 2005 a complete technology with a different set of solvers which is able to address different kinds of applications. You need to keep in mind that there is not one particular solvers which can really solve everything. And then we need to have access to a different set of solvers which will be really adapted to the applications that you would like to target. And then following the CST history, now we are part of Dassault Systèmes, and this allows us to enter multi-physics and multi-scale simulations to really approach also quite complex devices and complex systems as well. Regarding the technology itself, so the time domain solver, as well as the particle in cell solvers that I will also discuss during this session, is based on the finite integration technique. So the finite integration techniques, you can roughly see it as a generalized FDTD method. The main difference is here we are solving the Maxwell's equations in their integral formulation. And connecting this to the hexahedral mesh, then here you see that we have, compared to FDTD methods, we don't have anymore any staircase effect. So that means that we really have some accuracy enhancement compared to FDTD method. And with the number of mesh cells which are then reduced compared to FDTD method, then we can really compute accurate simulations within reasonable simulation times. An extension of the PBA techniques, which is this ability to have these capabilities in the hexahedral mesh grid, then we extend this to the TST technology, which is the thin sheet technology. You can have here an infinitely thin sheet, which is crossing over the mesh grid. This is also supported by the finite integration techniques, thanks to the integral formulation. About SIMULIA, starting from CST to SIMULIA, you have here the CST portfolio, which is then dedicated to several markets. We are really covering here the full spectrum from DC to terahertz applications. And now we embed all these applications into the industries. For the charged particle dynamics markets, we have 4 main industries that we can cover. And, oops, sorry. Oops. That we can cover. And here, for example, as I said, the aerospace and defense industry, the high-tech industry, the energy and material industry, and also the industries related to life science. This is exactly what I'm going to cover now in order to provide you with some examples that you can also use for your own applications. Let's now move on the different set of solvers that we have that you can use for your dedicated applications. So first of all, let's start with the tracking solvers. So the tracking solvers is a static solvers where you can use the external fields, which is an external E and external B field that you have in order to compute the trajectory of the particles. It's like having a picture of your simulation at a certain time where you see the particles, the particle trajectory within the external E and B field. We can also superimpose the space charge, and then in this case, the space charge is computed iteratively and superimposed to the external fields in order to take into account the whole effect that you have within the tracking solver. The applications that we can target here are related to electron gun design, bending magnets, mass spectrometer, and so on. And now regarding the particle in cell analysis, which is our so-called PIC solver. Here, this is a time domain solver. And the time domain solvers is the particle in cell solvers that we have is a self-consistent transient particle solvers, which takes into account at the same time the coupling between the Maxwell's equations and the equations of movement for the particles. And at each time step, we compute the Maxwell's equations. Then we modify the equation of movement for the particles, and then this is re-injected at the next time steps into the Maxwell's equations in order to drive and to perform the nonlinear effects that you have step by step into the simulation. The market which is addressed here are related to vacuum electron devices such as klystrons traveling with tubes, gyrotrons, and so on. We also have two other solvers in the Particle Studio Suite distribution, which is the electrostatic particle in cell solvers and the wake field analysis. Regarding the electrostatic particle in cell analysis, the difference that we have with the particle in cells that I've just described previously is here, it's not a self-consistent solvers, it computes the space charge versus time. So that means compared to the tracking that I have explained just a little bit before, it's like having a transient tracking analysis for your application. It's well suited for structures which are quite large with large time scales like plasma, where you have electrons which are then moving fast, whereas the ions are almost at rest. And then, of course, this has an effect on the time step, and the time step can really be here adapted also manually in order to control the convergence of the solver. There is no induced H field because this is not a self-consistent solvers, and that's well suited for plasma sources, electron gun with ionization, and so on. The wake field analysis, the wake field solver, is a transient solver with special beam excitations. So the beam is really the excitation, so that means that the input is the beam, and you only compute the wake field, so that means the electromagnetic fields which are then induced into the RF structures when the beam is passing through the RF components. And there is here, it supports relativistics as well as low beta beams, and that's well suited for accelerator components and beam position monitors. So all the diagnostics that you would have also to take into account for an accelerator, for instance. Let's now have a look to the different applications that we can target also with this technology. Let's first start with the aerospace and defense industry. Here you have an example which is related to communication and detection system performance. So you have the Earth, you can see on the picture on the right-hand side, and then you have a satellite, and the communication between the satellite and the Earth has to be performed with some high-powered devices which are then embedded into the satellite. For instance, here you have the so-called traveling wave tubes, which are then power amplifiers. And the design of a traveling wave tubes can fully be performed using CST Studio Suite. Here, for instance, you will need to use the peak solver because you need a self-consistent approach while the particle beam is propagating along the tube axis. Then you need to compute the interaction process that you have within the RF structure in order to calculate the gain and the amplifications that you have from a signal that you introduce in the input, which is then amplified along the beam and then extracted here in the output. This is exactly what the peak solvers can really perform to design such a structure. Another applications which is related to embedded electronics that you have in some certain systems and devices. For instance, a rocket. So then you have a rocket which is launched and from the Earth to the space, and then here you need to still keep the communication using the different components which are then embedded into the launcher, which needs to be also in a communication with the Earth. So that means that these components are active, and of course, depending on the different level of pressure that you have during the launching process, you might initiate a breakdown effect. So you have two different sorts of breakdown of RF breakdown analysis, which might occur in these conditions. The first one, depending on the different pressure level that you have during the launching process, you will have the corona effect. And as soon as the component is embedded into space, then under vacuum, you might also have the multipactor effect. The multipactor effect is the effect under vacuum when you have an electron which is accelerated by the local E field that you have into the device. These primary electrons can hit the walls, extract a secondary electron within the structures, and then which is then once again captured by the local fields and then create an avalanche effect, which might create then afterwards some damage for the passive component. Then I would like to provide you with some information about the tools that we have and the established products that we have for RF breakdown. You have, as I said, the multipactor analysis, which can then be performed using Spark 3D for fast and accurate simulations, taking into account the multi-carrier approach. So you can really use these tools directly in the same way as Carlos has mentioned it also yesterday, for those who were in the filter session. But for complex structures where you would like to take into account also more physics, then you can use CST Studio Suite with the space charge, which can be taken into account. You can even also import any external fields, and then you can then compute the multipactor analysis using whatever the peak solver or the ES-peak solver. Then you have the corona discharge. The corona discharge can be performed here using also Spark 3D. But if you have an RF breakdown at a pressure above 1 millibar, which is typically over 0.75 torr, then this is the area where you have to use Spark 3D only. On the other hand, if you have an RF breakdown that you would like to take into account at a lower pressure, which means below the 0.75 torr, then in this case, CST Studio Suite and the ES-peak solver is still suited to do these things, but because we have the ionizations and the Monte Carlo collision models, which are then also included in our models to do this kind of simulations. So the key benefits that we have here, if you would like, for instance, to take into account at a relatively low pressure, the effect about the multipactor analysis or the corona discharge, with CST Studio Suite, you are able to take both effects into account simultaneously. For instance, you will define the walls being capable of emitting the secondary electron emission for the multipactor approach, and you can also define a neutral gas at a certain pressure where you will also initiate the ionization in order to take into account the corona at the same time. The next topic is the propulsion system installation performance. And here, this is the so-called, for instance, plasma ion sources. And one of the plasma ion sources that we can take into account is the ion thrusters. You will have some more details in the next talks by my colleague Carlos, but I can already provide you here with some input regarding this simulation. So for instance, here we have a bit of plasma physics governed by an ESPIC solver, so the ESPIC solvers that I have introduced previously. And then the electrostatic calculations is performed with the space charge dynamics. That's well suited for large timescale simulations, and the ionizations of the neutral gas, plus the Monte Carlo collision models, which is superimposed also in this context, can also be taken into account. So you see here, you can create a plasma from a discharge into this plasma chamber, and then you extract the ions, and this process of extracting the ions can really create and provide with a thrust that you can then afterwards estimate also by the post-processing, because you have here formulations with a current that you can estimate to calculate the thrust. So this is something that we can also consider and take it into account if you are interested in designing such devices. Regarding defense and military applications, then we have vacuum electron devices in order to perform some analysis about radar systems, and the high power microwaves, which are then embedded into radar systems, are usually made of traveling wave tubes and magnetrons and klystrons. And this is something that you can perform also using the particle in cell solver. But you also have the so-called high power microwaves, which are then related to compact relativistic vacuum electron devices. And here, for instance, you have two examples. You have the magnetically insulated line oscillator. So this is an oscillator. You can see it like a linear magnetron, for instance. And then you have interactions here into these RF structures, which is able to generate a microwave to the output of the tube. We also have the so-called Vircator. Vircator design can also be done with our tools. Then you have here the high voltage generators, which is creating here high voltage pulse, which is propagating here. We have some electrons moving towards here a grid. And while the electrons are passing through the grids, they are creating here a virtual cathode, and the oscillations of the virtual cathode is then here capable of emitting a microwave pulse that we can then afterwards extract with the appropriate antenna. We also have here STREC cameras for night vision, and then this is only available with the tracking solver. And then we can also do photon-electron conversions, the so-called photoelectric effect that we can also take into account using the tracking solvers. So in other words, you have a photon beam which is hitting a photosensitive materials. From these photosensitive materials, you can then extract some electrons. Let's move on now to the applications related to energy and materials. So one of the main applications that we have behind the accelerator, the energy and materials industries is the accelerator community. So you see here you have an examples where we use the Wakefield solvers to calculate the electromagnetic fields induced into these 9 Tesla cavities, which is then considered here as an examples for a linear accelerator structure. And several facilities around the world can also be performed also using also this kind of technology. And that's really key to analyze here, especially when you are in the design phase, to analyze here the higher order modes, which can also be generated using the Wakefield solvers that you have also inside these cavities, to have a clear idea on how the design has to be performed in order to select the right modes and phase that you would need to keep the acceleration process for your particles. So several facilities around the world, such as linear accelerators, synchrotrons, colliders, and so on, which then will be used also to with the Wakefield solvers to do this kind of analysis. And of course, this is related to several applications, which could be fundamental research, materials characterization, spectroscopy, X-ray lithography, for synchrotrons, for instance, you will extract also some light that you will also try to use for some certain applications. And it can also be used for biology or molecular also analysis and so on. Any interactions that you would have between the light and the component. Here you have an examples where the Wakefield solvers can be used. And you have two different kinds of applications related to accelerator components. On the left-hand side, you have the instrumentation, and on the right-hand side, you have the component design. Regarding the instrumentation, everything is already set, but you need to access the beam characteristics. And this can be performed by applying the so-called beam position monitor. And at these particular locations, when the beam is passing through the vicinity of these beam position monitors, then you can capture the signal and analyze the beam properties if everything is then set properly for your application. So this is here a diagnostics, which is then very useful to understand here the properties of the beam. Regarding now the component design, you can also use the Wakefield solvers in order to analyze what are the different modes or wake fields which are then generated into particular structures such as collimator or pillbox cavities. So you have, for instance, here on the right-hand side, you have the Wakefield signals that you can then estimate out of the structure. And if you do a fast Fourier transform of this signal, then you can directly analyze if you have any mode competition and so on, which would also affect the whole acceleration process for the structure. So this can really be fully analyzed, and you can do here some virtual prototyping in order to really design properly the accelerator component design. Another applications related to energy and materials is the plasma for fusion. You have here a new source of energy production, which is the controlled thermonuclear fusion, which is created here for these particular examples by the magnetically confined plasma. For this type of structures, you have many components and many physics involved, for which the simulations can really be here helpful for the dimension of the different parts of the complex structure. For instance, the plasma needs to be maintained confined in such structures, and the complex magnetic coils, and as well as all the components which are then related to the magnetic fields, can really be designed and analyzed with the simulation tools. The plasma needs to be also sufficiently hot to maintain the thermonuclear reactions. Even if we are not going to take into account the thermonuclear reactions, the devices or the process which is able to maintain the plasma sufficiently hot can also be studied using the simulation tools. For instance, you might have sometimes also this kind of devices which could be also heated and sufficiently hot using gyrotron. And the gyrotrons can fully be designed also using the PIC solver of CST Particle Studio. But you also have sometimes some beams which are then introduced into the device, and these beams coming from whatever linear accelerators and so on, or even ion sources, can also be fully designed using CST Particle Studio as well. So you see there is the choice of power, and the choice of power for the right application. And here you have a set of devices that you can use on demand that you can also fully control using the simulation. On the other hand, the output power is limited by the technology. You see, there is a compromise between the frequency, the operating frequency, and the average power that you can use also and for the design of your structure. So, for instance, if we start from the bottom left here of this graph, you have here the solid state devices which are used for compact and low power applications. And of course, the power is in this case limited. If you want to increase the power for some certain frequency range, then you need to change the technology. And then in this case, you will use the vacuum electron devices, which will be performed for the applications that you would like to target. If you increase the level of power and if you move slightly also to increase the frequency range, then in this case, you have different kinds of applications where you will see traveling wave tubes, klystrons, and so on, which are then structures working as broadband devices. But then if they are going to interact on some frequencies which are then larger, so that means it's not a single frequency, but they are going to interact on a frequency range which is defined, then in this case, you see that the power will be limited because the power is distributed over all these frequency range defined. So vacuum electron devices allow increasing the output power, and the broadband behavior limits the output power. So if you would like to increase the power that you would have, for instance, for ultra-wideband antenna or directed energy weapons, so you see that you can really increase the power, then in this case, you can only work at a particular frequency. High-power microwave devices operate at a single frequency, and the high power here is limited by the plasma formation and the breakdown analysis, which also might occur in the device because of the power which is embedded into the structure. And you also have some research activities, the research activities such as linear accelerators and fusion heating. So all the applications that we've seen previously, which are also then embedded into this graph, which needs to be also designed for specific applications, of course, taking into account all the limitations that we've seen here for the simulations of this kind of devices. Let's now move on to the applications related to the high-tech industry. Since we have the capabilities of doing some plasma physics, so the plasma that we are considering is a plasma dominated by the collisions, working at low pressure, and we can also take into account the Monte Carlo collision models to perform such application. So then that's here the design of so-called ICP or CCP reactors, inductive coupled plasma, capacitive coupled plasma reactors. And for this, we can here control the plasma dynamics. You can control the ion beam profile, and you can also, because you can set here the external systems such as the coils and so on, you can also analyze the plasma confinement and homogeneity, which is key for this kind of applications. And this can be controlled with the coil design and all the systems which are then surrounding the plasma reactor itself. So you have here a complete reactor design for process optimization. The ionization of the background neutral gas can be performed. You can really initiate the discharge and then see how the plasma behaves into the structure. The neutral gas excitations as well as the elastic collisions are taken into account. Then you can really here analyze the kinetic of the plasma and dominated by the collisions. And you can estimate and predict the ion density profiles, electron and ion density profiles that you have within the plasma. For this, once again, we also have a technology, a particular technology on demand that you can also use. We can distinguish two approaches. There is the macroscopic behavior and the microscopic behavior. For the macroscopic behavior, we can use CST Studio Suite and Microwave Studio, where the plasma is treated as a bulk. So that means that you can use both the time domain and the frequency domain solvers for using and controlling here the plasma, which is then described as a dispersion model. So the dispersion model is then entered in the tool, and you describe your plasma as a bulk. Your plasma is also, in this case, a load. So that means that you can also connect this to any matching networks in order to adapt and to match the matching network to the plasma chamber in order to perform the whole analysis without plasma and analyzing the effect in the presence of plasma to see any frequency shift that you might also have in this context. So for instance, one of the dispersion models which can then be used is the Drude dispersion models, which can be linear or non-linear. I will talk about this a bit later during the semiconductor manufacturing talk, and then you will see how this can be used. If you have also the applications of a constant magnetic field, which then needs to be also superimposed to the process, then this is something that you can do with the gyrotropic dispersion model. So this was for the microscopic behavior when the plasma is treated as a bulk. For the applications regarding the microscopic behavior, then we are going in this case to compute the space charge dynamics, and we are going to use CST Particle Studio for doing this. So here we are considering in the background the neutral gas, and the neutral gas will be ionized in order to extract and to analyze the production of ions that you will have out of the structure. Then we can consider here the Monte Carlo collision models, which is then the elastic collisions, the excitation of the neutral gas. Then we are going to perform a full space charge interaction directly from the discharge to the plasma established regime. We can fully control how the plasma is established into the plasma chamber, and the ESPIC solvers is well suited for this kind of application. This is the workflow that we have for the plasma reactor devices. So you start with a certain geometry, and then can be whatever your CCP or ICP reactor. Then you have here the design that you can directly use. You can also perform your own design. Then as a second step, you take into account the external sources with the time varying potentials. Here you have the potentials at 13.56 megahertz, which needs to be taken into account in order to maintain the discharge within the plasma chamber. And as a third step, you take into account the ionization of the neutral gas by applying the RF voltages. And here you have the choice of the gas that you can use for your applications, which are then usually noble gases like argon, helium, neon, and so on. And then you can here use the Monte Carlo collision models. So once again, the plasma is treated as a kinetic model and dominated by the collisions. Then you can run the ESPIC solvers, well suited for this kind of application. And then you can have such figure that you can analyze, where you have here, for instance, the ion density profile, where you can control the plasma homogeneity and uniformity. Then, of course, within this loop, you can reach here in step 6, the plasma reactor optimization performance for what you are interested in. And at the end, when you apply also the a bias DC voltage, then you can extract here the ions you are interested for your etching process. And then here the materials are removed by the ion acceleration across the plasma sheath. Another example that we have also in the context of high tech is, for instance, the neutron generation tube. And more specifically, this is the design of the so-called ion sources. So how does that work here for these particular applications? This is, for example, for the productions of neutrons out of this device. Here can be an applications related to in situ measurements for mining and oil detection, for instance, can also be used for explosive detection or neutron radiography. We don't take into account the extractions of neutrons, but the device which is capable to then producing the neutrons afterwards can fully be performed and analyzed with CST Studio Suite. So here you have an ion source where you have here you start with a certain gas. Here This is a gas which is constituted of deuterium and tritiums in order to take into account already the neutron into the species in the beginning. Then you compute the discharge, and then you create electrons and ions. And if it's properly done, you have here some voltages which are then applied. You can then extract the ions. So the ions are then made of deuterium and tritium ions. And then they are then propagating and accelerated towards the tube, and then hit the target, where you can also take into account the emission of secondary electrons from the ion impact over the target. So you have here a full energy distribution that you can analyze. So then you can also estimate finally the energy that you will have, or the power that you will have for the neutron extraction, even if we don't take into account the neutron beam. So this is one particular example where ion sources can be used, and then you can control here the whole device, and then do this kind of simulations with the high predictions that you can do also with the simulation. Another application is the applications related to the microwave oven technology. You have here, for instance, on the right-hand side, you have an example of a magnetron. So the magnetrons can fully be done using our simulation tools, and here you can analyze the whole behavior. So the power source of the microwave oven is the magnetron. The magnetron is an oscillator, is a cross-field device, and the energy is transferred from the rotating e-beam to the magnetron cavity, which is here the RF structures constituted here of 10 coupled cavities. And the power extractions characterize the microwave radiation. And the microwave radiations can then be, the magnetrons is then coupled here to the microwave oven cavity. And here you have usually some waveguide and antennas, which guides you then directly with the radiations, which is then afterwards connected to the microwave ovens, and then you can nicely see afterwards what are the different modes which are then generated into the microwave oven cavity. The microwave output power generated here out of the magnetrons depend on the geometry, and this can be fully parameterized and analyzed in order to optimize the efficiency of the magnetrons that you can control and predict by the simulation tools. The performance of the microwave ovens depends on the coupling between the power source and the oven cavity. And of course, from a pure RF analysis, you can also figure out, by calculating the Q factors and so on, you can figure out what is the best coupling that we need to introduce to match the RF systems to the magnetron geometry. Let's now move on to the next applications, which are then related to life science. One of the main applications that we have related to life science are the medical linear accelerators. So for instance, you can see on the picture here on the left-hand side, then you have here linear accelerators, which is embedded into such a structure. You have an electron gun somewhere, and this electron gun that you have here in this area is going to introduce some particles which are then accelerated toward the linear accelerators. Then they are going to hit a target to produce afterwards X-rays or gamma rays, depending on what you are interested in for the diagnostics and so on that you would like to perform afterwards. So how does that work? So we can really completely fully perform this kind of simulation. You introduce here a DC beam, which is coming from an electron gun somewhere a little bit here in this area. Then the particles are seeing here the phase of the electric field, and while moving, they see an accelerating phase, which is the case here. You see the beams moving because they are always seeing an accelerating phase for the particles, while they also have here the changing phase, which acts on the particles as a decelerating phase also for the particles. So some particles are accelerating, whereas some of them are decelerating, depending on the phase that they are seeing also for from the RF fields. So this can also be fully parameterized and optimized in order to get the right energy, the right amount of energy that you need, because these particles will then hit the target, and then you will have to get the right amount of energy that you have when you are going to use the X-ray or the gamma rays for the application. So you've seen here different kinds of applications related to different industries. And let's now summarize and extract the key strengths that we have that you can afterwards use for your own application. So first of all, and this is key, we have a set of solvers that you can use on demand for a complete technology. You've seen the tracking solvers, the particle in cell solvers, the electrostatic particle in cells, and the Wakefield solver. So many applications transverse to several industries. So you can really address the whole market dealing with particles. You can do virtual prototyping, and then you can address here the industries which are then related to aerospace and defense, energy and materials, high-tech, and life science, which are really the main 4 industries that we have. It enables simulations of complex problems and structures, such as large-scale environments, such as accelerators, for instance, but you can also analyze complex physical devices, such as vacuum electron devices, and here you can really do some real virtual prototyping. That's exactly what I'm going also to show you when I will present the capabilities related to vacuum electron devices. And last but not least, it enables also the development of new technologies, for instance, plasma physics. Then you can really analyze what's going on into a plasma reactors for semiconductor manufacturing equipment, especially when you have no diagnostics. So you can already figure out how it behaves. And you can also analyze new physical concepts, like, for instance, new materials, new compact devices, or new electronic components that you can also fully design with our simulation tools. So with that, thank you for your attention, and I'm open for the questions.